Okay, so let's see what we have so far. We start with position. And we call that x. And the unit is meters. By taking the derivative, we can change it to velocity or speed, which is v is equal to the derivative of displacement, and that's going to be meters per second. And we take the derivative of velocity, the rate at which your speed is changing, and we have acceleration. And that is, acceleration is dv dt, the rate of change of velocity, or it's the second derivative of displacement. And those units are going to be meters per second, or meters per second squared. So what happens if we multiply by mass, kilograms? Meter kilograms really has no meaning to us right now. How about mass times velocity though? Mass times velocity is momentum, and that's going to be in kilogram meters per second. So by multiplying by mass, velocity becomes momentum. How about acceleration? Oh right, mass times acceleration is force. Right, the force you put on something is necessary to accelerate it. You put no force on something and it just continues along at the same speed, like that rock floating by you in space with no force. But if you put a force on it, you can change its speed. And so this is going to be a kilogram meters per second squared. So force is mass times acceleration is kilogram meters per second squared. We call this a Newton after Isaac Newton. Okay, something interesting we get from this is that force is the time derivative, this is our time derivative direction. Force is the time derivative of momentum. Is that true? Force is equal to dp dt. Sure, you're pushing a car. The harder you push the car, you have a frictionless car here, right? And you push it as hard as you can. The harder you push it, the faster you can change its momentum. Force is equal to the rate of change in momentum. Or the change in momentum is a force times the amount of time you're pushing on that car. So you push it for a long time really hard, you get a lot of momentum going. Now, what if you stop that car a really short period of time? You get the same change of momentum with a really short time. You get a huge force. Let's say you put this brick wall here, right? And you stand right here. And you know that that car is going to stop. You're going to absorb all that momentum with your belly in a very short time. It's going to require a huge force. I don't think that would be good for you. And let's not do that. Okay, then we have energy. Let's explore energy. If you're moving, you have kinetic energy. And so kinetic energy is 1/2 mass times velocity squared. From your position, right, if you move something from down here to up here, you've increased its potential energy, which we've already talked about can turn back to kinetic energy if you let it drop. But your potential energy is mgh, mass times gravity times height. You can also have potential energy in a spring. If you're pulling a spring, potential energy in a spring is 1/2 kx squared, where this is a spring constant. That would be newtons per meter. That means like if it's 1,000 newtons per meter, you get 1,000 newtons of force out of it for every meter you stretch it. Stretch it 2 meters, you get 2,000 newtons. Okay, so these are different. This would be gravitational potential energy. This would be spring potential energy. How about the units? The units of energy is a joule, right? Or we abbreviate it as J. And what should that be? Well, how about this? This would be kilograms, meters per second squared. So that would be kilogram meters squared per second squared. How's that? How about this? This would be, we think they're all the same. It's all the same substance, right? All the same thing. If it's all energy. This could be kilogram meters per second squared. G is acceleration, right? Meters per second squared times height, which is a meter. Yes, very nice, okay? Kilogram meters per second squared. However, we could also go back and see this, meter per second squared. We could see that this is a Newton. Kilogram meters per second squared is a Newton. And this is a meter. A Newton meter, is that the same as a joule? Well, I mean, we can see that it is. Kilogram meters per second squared times meter is kilogram meters squared per second squared. But also, this is interesting, because this is a unit of force, and this is a unit of distance, right? And so, with a force over a distance, you can be giving energy to something. Of course, work is equal to force times distance, so the unit should work too. Lastly, this is, let's put the units down here. This would be newtons per meter times x squared, and that would be meters squared. Cancel your meters, and you have a Newton meter. Again, a Newton meter is work, or we can see a Newton, kilogram meters per second squared, gives me kilogram meters squared per second squared. Or again, we could see a Newton is a kilogram meter per second squared times a meter is a kilogram meter squared per second squared is a joule. So all of this is energy. And let's say you want to change your energy. Let's say you want that car to get pushed up this hill some distance h, and you want it to move fast. You want to change its potential energy in a short period of time. You're going to need a lot of power, right? And so power is the time rate of change of your energy. Power equals, that's a capital P as opposed to a small p for momentum. Power is dE dt, how fast you're changing the energy. So for instance, this car, I could, with a very small, unpowerful motor, I could get it all the way up that hill with the right gearing. But it would take a long, long time because the power is small. But if I want to get it up there fast, if I want a lot of change of energy with a short period of time, I'm going to need a lot of power. And what are those units? That's going to be joules per second. And what's a joule per second? It's a what? It's a watt, named after James Watt. And what is that? A joule is a kilogram meters squared per second squared. So a watt is a joule per second. So that would be second cubed. Let's finish it up. This is power, and this is your time derivative of power. Your time derivative of energy is power. So just from these derivatives, position, first derivative velocity, second derivative acceleration, we were able to make a connection to force and momentum, and force is the first derivative of momentum. And then we were able to get kinetic energy, or we were able to get energy out of velocity and out of position. And the time rate of change of that energy is our power. Hope you like it.